In this video, we're going to work with complex fractions. And complex fraction is just basically a situation where we have fractions within fractions. Now, what I want to do here is talk about a couple different methods for simplifying complex fractions. Now, the first one is to just understand that a fraction bar means the same thing as division. So if I look at this, 4/5 over 8/15, that fraction bar right there is just me saying I'm going to divide. So I can say divided by 8/15. And anytime you're dividing by a fraction, that's going to be the same thing as multiplying by the reciprocal or the flip. And then once that happens, you can do your normal reducing. Divide by 5, divide by 4, and so this complex fraction simplifies to 3/2. All right. And we can do the same thing here in example 17, where we've got some letters as well. So this is 3a divided by 25b squared divided by 9a squared over 5b. But I know that that's the same thing as multiplying by 5b over 9a squared. So I can cancel this 3 and this 9, cancel this a with one of the a's here, cancel this 5, divide by 5, divide by 5, and then divide by b, divide by b. So I end up with 5 times b times 3 times a on the bottom. So that would be 15ab, and then on top just 1. All right. Now there's another method, but actually, you know what? Before we talk about method 2, let's approach example 18 using method 1. So I think we have just enough space here maybe. I'm going to put a kind of a dividing line here. And we'll say method 1 over here. So the one from the previous page. And I'd encourage you to maybe press pause and try method 1 on this before you watch the video. But what we should have is 4 over x plus 3 divided by x over x squared minus 9. But that's going to be the same as 4 over x plus 3 times x squared minus 9 over x. Now, we know that in order to do any kind of canceling, everything has to be factored, right? So the x squared minus 9 needs to factor into x plus 3, x minus 3 as a difference of squares. And then I can cancel out my x plus 3's. So I'm left with 4 times x minus 3 over x, and then I could go ahead and, 4x minus 12 over x. So there's our simplified answer there. Now method 2, though, still what we're going to do here is, instead of turning it into a division problem, we're going to multiply the numerator and denominator of the complex fraction by the least common denominator of all fractions appearing. Okay, so here's what that means. The denominator of the top fraction is x plus 3, and the denominator of the bottom fraction is x squared minus 9. So what I'm going to do here in method 2 is first I'm going to find the LCD. Now in order to find the LCD, I better go ahead and factor the x squared minus 9, just like we did using the other method. So I can see that my least common denominator should be x plus 3 times x minus 3. So that means what I'm going to do now is it says multiply the numerator and denominator of the complex fraction. So that means the big numerator, the big denominator, by the LCD. So I'm going to multiply this by x plus 3 times x minus 3. You know, and I can put this over 1 just to make it really clear. This is multiplying to the top here. And x plus 3 times x minus 3 over 1. That's still legal because we have this big fraction here, and I'm doing the same thing to the top and bottom of this big fraction. But of course, what this does for me is it makes it so the fraction within the fraction disappears on bottom, and the fraction within the fraction also disappears on top. So all I'm left with is on top 4x minus 3 over 1 divided by x over 1. And of course, if you have something over 1, you don't need the over 1 part, so it would just be 4 times x minus 3 over x, just like we got here. All right. And again, here's let's do both methods here too. I think this is really worth making sure we understand both, because you'll see both throughout your mathematical career here. You might even see both as you do homework. So method one. Method one, in this instance, we got a little more work to do, okay? And here's why. In order to be able to take the top fraction divided by the bottom fraction, I have to have the top and bottom being just one single fraction in order to do this. So method one, I can't really make any progress until I get the fractions on top together and the fractions on bottom together. So in order to make a least common denominator on top, I need to multiply by x on top and bottom of that fraction and by y on top and bottom of that fraction. So that gives me x squared over yx minus y squared over yx. Okay, I have to do the same thing on bottom. I've got to say, well, my least common denominator down here is going, oh, I'm sorry, went on autopilot there, is going to be x squared times y squared, so here I need to multiply by x squared on top and bottom. So we end up with y squared minus x squared. Oh, sorry, jumping the gun. Over x squared y squared, x squared y squared. Okay, so then I can combine to say this is x squared minus y squared divided by yx over y squared minus x squared over x squared y squared. So now I finally, after quite a bit of work, finally have it looking like example 17 here, where it was just a fraction divided by a fraction. So now I can do that. And then, of course, we see that division, so we turn it to multiplication. Okay, now I can definitely see some simplification that can happen here and here, right? Cancel this with one of those y's. Cancel this x with one of those x's. Now this and this are not the same, but they look very similar, right? So understand this is another situation where they're just opposites. So what I can do is maybe up in this fraction, I can pull a negative out. And then I can go ahead and say, all right, that will cancel with that. So my final answer is negative xy. So quite a bit of work to do that one. Now, this is one where method 2, I think, ends up being far superior, a lot easier. The one thing that's a little bit confusing is we had to deal with least common denominators using method 1, and we found that our least common denominator was x times y. But in this instance, when we're doing method 2, when we talk about the least common denominator, we're talking about the least common denominator for everything. So the least common denominator for all the fractions, ones on top and ones on bottom, well, it would just be the different factors I see raised to the power of the most number of times they appear. So the LCD in this case would be x to the power of 2, because it appears twice in that denominator, times y to the power of 2, since it appears twice here. But then once you do that, the rest of it's a lot more friendly than the last one. I'm going to multiply by that on the top and on the bottom. And when I do, what I get is up on top, x cubed, y squared over y, minus y over, x squared y cubed over x, divided by x squared y squared over x squared, minus x squared y squared over y squared. And so right off the bat, I can cancel these x squareds. I can cancel these y squareds. So now there's no more denominator, no more fractions in the denominator. I can cancel this y with one of those y's. I can cancel this x with one of those x's. So now I'm left with x cubed y minus xy cubed over y squared minus x squared. And what I can do is I can factor out, I can see there's an x and a y common to both terms, leaving me with x squared minus y squared, which again, like in the last one, is almost the same as what's on the bottom. So then if I just pull out a negative, that would do the trick. Sorry, when I originally created these notes, I wasn't really planning on doing both methods on both these examples, so I probably did not leave you quite enough space, so I apologize for that. We can go ahead and cross those out now. You, of course, get the same answer. All right, so complex fractions are tough. You know, one like we just did is probably not going to appear on an assessment. You know, we just have other things to do. But it is important to understand this the idea of being able to apply this methodology for simplifying down a complex fraction. That is something that you're going to use in this class and in future classes as well.